and then you can start whenever you're ready.
Okay, thank you. And you can see the screen now.
Yep, I can see the screen.
You can see the PowerPoint.
Yep.
Okay, we're going.
All right.
Well, thank you, Amos, and thanks for other staff, Kurt and others at Mount Rainier National Park for allowing me to do this presentation today. It's a little bit different from our usual fare. Usually at this time we would be pulling a lot of rocks out of boxes and setting them on tables, maps, and even Oreo cookies. So this is a little bit different. We'll have to do a PowerPoint and not do lots of activities, and that's of course, a little disappointing, but I've tried to give you some ideas throughout this coming talk about activities you can do with some of the visitors at Mount Rainier National Park. So, so we'll just move on here, and I think, let's see, I might try widening the screen just a little bit right here. Well, I guess it's just going to be as it is. So, all right. Well, I think first thing that people need to know, and especially if you're not from this area, you already recognize it if you are, Mount Rainier is really the spiritual and cultural icon of the Pacific Northwest, especially Washington State. There are 5 big volcanoes in Washington State, and each one of them has this kind of its tributary populations, people that follow it. But just overall, Mount Rainier is seen as the biggest and, by some the most beautiful. But all of these volcanoes are like big gleaming white magnets that attract people, and that's during times of calm and times of volcanic crisis as well. So Mount Rainier really shapes this area's identity, and it's kind of the branding of the Pacific Northwest. And so when you talk about Mount Rainier, you have to realize that everybody feels a sense of ownership and identify it a lot with it. People see it on the horizon from the Puget Sound area. Many times they may set their mood for the day by whether they can see the mountain or not. So we're going to talk about the geology of Mount Rainier, how it was formed, some of the interpretive messages that you give to people. I'm not going to give you every bit of detail that we know about Mount Rainier, but the important messages that I think will be helpful to you when talking about the volcano. So this is, of course, just answering basic questions. There are other materials available I'll discuss in a moment. You should feel confident and competent that you have the information that you need to answer those basic questions. That's my goal for this presentation. And there we go with some historical postcards noting that Mount Rainier is this cultural icon of the Pacific Northwest. So we will start with the basics right now. This is probably going to take 45 minutes or so. And you can stop and start, I guess, whenever you want. Here we go. So some basics. What should you as a park employee know about Mount Rainier? And, if you learn nothing else from this, learn these basic facts, that it is a volcano. It's not erupting now, but it is still a volcano. Mount Rainier built a landscape that people live on in the lowlands and in some of the upper lands near the volcano as well. It's considered one of the most hazardous volcanoes in the United States, not because it's particularly explosive, but because, or that it's overdue or anything like that, it's not, but because of its large proximity, or it's being large and its proximity to big populations. We know that Mount Rainier will erupt again, and even a burp is going to be a big deal for all of us in the Puget Sound region. And the same processes that built this volcano are hazards during future eruptions. So you should know too, you'll hear from Scott Beeson, I think, concerning debris flows that in the park, that there are hazards, geologic hazards in the park beyond what happens during a volcanic eruption. Okay, so we have put this information into modules. I put the talk into these different modules that you can look at the various parts or go back over them as you wish. And Okay, let's start. Well, let's see, go back here and just say, we'll start with talking about the Cascadia subduction zone, zoom through time, what has happened through time at Mount Rainier, and then look at some volcanic processes, how the glaciers are architects of the volcano, it turns out. Look at some volcanic features at Mount Rainier, and then looking at messages, volcanic hazards, and the messages that we give to people. So, some of you know that I have uh, worked on various aspects of these situations, everything from glaciers to debris flows to volcano hazards and volcano hazards communication. So hopefully some of the best of what I can give you is in here, and you can transfer that on to visitors. One of the things that the USGS and the National Park Service worked on for the better part of a decade was an educator's guide with emphasis on Mount Rainier. And this was done through park education staff. We had a couple dozen teachers involved from the Puget Sound area. They're basically the ones who asked for this. And so some of the activities that I would normally do with you, if we were in the Longmire Community Building, for example, some of those are in this activity, this educator guide. So I'll make light of them. So you can see the address for it right there and go check it out on your own as you wish. Okay, so let's start with module number 1, noting that there is a hidden force, the Cascadia subduction zone, that drives the formation of volcanoes. And there's a difference in density between rocks on under the ocean and those under the continents. And so the Earth surface is always evolving, but we realize that what's happening at right off the coast of Washington and Oregon, Northern California, is making the Cascade volcano. So, all right, note here that we have all these different plates, and then we have it's the boundaries of these plates and how these plates interact, which causes a subduction zone to form. We'll define subduction zone in a few minutes. Right, but it will be helpful for you to know that there is convection going on inside Earth's interior, and so we have heat, warmer rocks, rising, and cooler rocks falling down, so to say, deeper into the surface, below the surface, and maybe it's a little bit like water in a beaker over a little Bunsen burner. So these are the forces that are driving us, driving the movement of these big tectonic plates. Okay, plate tectonics. So now we're going to look at those different plate boundaries. I said that they were so important. All right, so if we were together, you'd all be having Oreo cookies, and each of you would be asked to twist off the top, break the top piece in half, and move the broken top around as illustrated in these next 3 slides. So we can show what happens when 2 plates move apart. And that is what we see on the right diagram. And then on the left, you can see that we've pulled the cookie apart, and you can actually see mantle rock, the top being the crust, the chewy interior, the creamy interior being the Earth's mantle. So we have rocks from, really the top of the mantle coming up at various places where the different plates are being pulled apart. And those are called divergent plate boundaries. And one example is in the Pacific Ocean, about 100 miles, or actually about 300 miles off the coast. Transform plate boundaries. Now, in this way, we have one tectonic plate moving past the other, and you can show that in hand motions. You can do it with your Oreo cookie as well, where you move the top piece one past the other. We have these transform plate boundaries happening in the San Andreas Fault, California. We have it happening 300 miles off the coast, where all these spreading zones where magma is coming up are being offset. All right, and then we have the third type. It's called a convergent plate boundary. excuse the phone. The convergent plate boundaries are where we have two plates moving together. So you can illustrate this with your hands, oops, coming together, your fists coming together. And sometimes we have one of the plates being more dense, like the oceanic plate being more dense, and so it's actually diving beneath North America. You can show it in this way, and you can show it with the cookie as well by rearranging the top cookie on its base. So there we have the three different kinds of plate boundaries: the transform, the convergent, and the divergent. You can try this on your own, of course, then you're welcome to eat those cookies. So it's a good reason for you to run down to Ashford and get some cookies, right? Okay, so again, we have all three of these plate types at just off the coast and underneath and beside the state of Washington, Oregon, Northern California. And the interesting thing is, you can see this line that I'm pointing to, this convergent plate boundary. It's actually the trench. It's actually where the oceanic plate is diving beneath North America. Okay, and so in about 100 miles inland, notice that we have a somewhat parallel arc of volcanoes. And you can see that that's because the magma is being formed when we have the rocks reaching sufficient depth so that it melts. So we have magma melts right underneath each of these volcanoes. And I do mean that under each of the volcanoes. We don't have a big, long bathtub-like trench of magma under there. Please try to dispel that notion. But we have more like soda straws reaching down from each of these volcanoes to pods of magma rising below the surface. Okay, now I think that we'll see if this is, yes, we can make this work. All right, so here's a little video clip that you should have, and you are welcome to use in your interpretation. It shows what's happening in the Pacific Northwest, and assembled by a group called IRIS education group. So you can see there we have the spreading of the plates. We have these two plates moving apart in a divergent way right over here. And here we have the subduction at a roughly 42-degree angle or so. And then doing a close-up on Washington State, we can see these pods of magma that are rising. They're warmer, they're less dense than the surrounding rock, and so they are rising, and pop, they hit the surface, and there we have a volcano erupting. That one's showing Mount Hood there. The same thing happens with Mount Rainier, St. Helens, Hood, Glacier Peak, and Mount Baker. So I'm going to run it by one more time and point out something else too. So you see that little green earthquake happening, several earthquakes showing where earthquakes happen. But notice as the Juan de Fuca plate, this very dense plate, moves towards North America, it actually raises some of the land right on the coast. And so that is what we know of as the Coast Range in Oregon, southern Washington, and the Olympic Mountains in the north. So in case you're wondering, the Olympics, the Coast Range basically consist of a lot of volcanic rocks, but they are old volcanic rocks that they're not actually volcanoes in themselves. They're rocks that have been lifted from the ocean floor. Okay, let's move on. I am just super excited to show you this next graphic that I just found. And ta-da! There it is. It's another way to illustrate a subduction zone. And notice this great baking project. And I hope that any of you watching this who try this will actually get in touch with me and let me know and send me some pictures of it, okay? So here we go. So we have the lower mantle and the upper mantle that is very, it's very, very plastic. And so it bends a little bit, but then we have the oceanic crust dipping down and going down into the Earth's mantle. We have this less dense and actually forget the garlic there. That's a piece of garlic. But we have a less dense crust that is actually being lifted and buoyed upward by the movement of more dense rock beneath it. So here we have the Olympics being scraped up here. We have this low region, the Puget Sound lowlands, then we have the Cascade Range. So that's a pretty neat illustration, isn't it? Okay, so let's look at 5 interpretive messages from this section, things that you can tell your visitors about the Cascadia subduction zone. The one is that it's a hidden force behind the eruptions at the Cascade volcanoes. Uh, you can't see it. You can feel it when there's an earthquake, but it is moving. The oceanic plate is moving at about 2 inches or so a year beneath North America, and of course the heat, the pressure is causing magma formation 100 miles inland and causing magma to rise and volcanoes to erupt. Okay, it's just one of many. The Cascadia subduction zone is one of many. We have a subduction zone off of the Aleutian Islands, off of the coast of Japan, down by Indonesia as well. So the entire Pacific Ocean is actually rimmed with these subduction zones, and that's why we have a ring of fire, we have a ring of volcanoes around the Pacific. This was such a mystery to people for centuries, and now just in the last 50 years or so, we've figured that out. Okay, so magma forms at the top of the subducting slab. It's forming right now, even as we sit here and watch. As long as there's subduction going on, there's going to be volcanoes erupting in the Pacific Northwest. So expect more volcanic eruptions. Other earth movements happen because of them as well, such as earthquakes and tsunamis. Okay, and if you want, whoops, you can go to the Surrounded by Volcanoes activity in the Mount Rainier Educator Guide, and you can actually plot the earthquakes, which show the the show the boundary between the crust and the subducted slab of oceanic rock. Okay, the second module will say that let's look at the previous volcanic occupants. This will be a zoom through time at Mount Rainier, looking at the volcanism that has taken place here in the past. And that is one of the key messages, that Mount Rainier is not the first volcanic occupant of this terrain. It's just the most recent. So long before Mount Rainier was constructed, volcanoes were here on the landscape. And we're going to look at some of the evidence. Okay, so for example, and I'm just going to give you a few quick slides here, and then I'm going to summarize it in one graphic, and of course you can go back and look at it later. Uh, but about 56 to 49 million years ago, we know that there was some sort of an inland sea here. We know that volcanoes were erupting through the sea and making these pillow basalts, similar to what we see off the coast of Hawaii being built today. And then after that, we had other volcanism, other volcanoes happening. We don't even see any evidence remaining of their cones, but we know that there's lots of fragmental debris, rock debris, that remains. And we see that in the Johanna-Koch Formation. So, okay, raise your hand if you've been over to Panhandle Gap. Anybody? Yeah, yep. You've seen the beautiful purpley rocks over there that are shown in this little picture. Those are from the Johanna-Koch Formation. We also have a big caldera to the east of Mount Rainier National Park. And that had, big mega eruptions, and lots of stuff was tossed out of that. And that's created the Fikes Peak Formation. More could be said about that, but enough for now. So, at the same time, we had this inland sea, we had some sandy beaches as well. And so we do have, especially in the northern part of the park, we have some nice sandstone just north of the park. There's coal beds, and so not everything is volcanic. But anyway, let's move back to volcanics. So at about 17 million years ago, oh my gosh, we had a lot of igneous rock. We had a lot of magma pile up under the Earth's surface, and it stalled several miles down. It just stalled. It didn't have enough oomph to punch through to the surface. So it just cooled in place. And we know that as a Tatoosh pluton in the Tatoosh Range, which is on the south side of Mount Rainier National Park. And then forces to the east started doing strange things. We started having these very effusive, very fluid lava flows coming through rifts right on the Washington, Oregon, and Idaho border right here. And that lava flowed for millions of years across Washington state, and it even came probably, it's not clear how it didn't just flow through the Columbia Gorge. That wasn't there at the time, actually, but it probably became subsurface and actually went out to the coast and created a lot of the basalts that we see there today. So, okay, now the Olympics. I know a lot of you are familiar with them. It's another part of the National Park Service, but again, as noted before, the lava's there. Are scraped up off of the ocean floor and were raised high because they were crumpled. The surface rocks were crumpled during um, the subduction process. So they're lifted high, and I like to think of the Olympics as being, like on this, just the marshmallows floating on the top of the hot chocolate, and they get lifted to the top. They're always going to rise to the top. And of course, there were other things going on too, like these larger forces were uplifting the Cascade Range. It's not the volcanoes, but the larger, broader Range rock. So that's been happening since about 13 million years ago to the present. So there's pressure from the west, pressure from the east, pressure from beneath, pressure from the south, and it's all leading to a complex series of, uh, of interactions and the raising of the Cascade Range, and it's all keeping this area geologically fresh. All right, and finally at the top of the heap, we have Mount Rainier and Mount Adams and St. Helens and all the Cascade volcanoes we talked about before. So at a place like Panorama Point, it's terrific to go there. It's a great place for you to go and for you to show to people that on the horizon, way off in the distance, to the left of Mount. Well, let me see, where would that be? I guess it's going to be just in this general area, maybe this direction, actually, a little to the southeast. You're going to be able to see the uplifted Columbia River basalts. And you can see the Tatoosh Pluton in the distance. Here it is, Tatoosh Range. And you can see the young volcanics as well of these volcanoes. All right, so now let's go into a different scale. Now we're going to move to, what's happened just with the building of Mount Rainier. And uh, one of the things that's help you understand kind of the nature of volcano and mountain building is that Mount Rainier grew in alternating stages, sometimes with, really high eruption rates with lots of lava and ash coming out, and other times with less so. So it all started maybe 600, 500,000 years ago. And you can see that between about roughly between 500,000 400,000, we had a lot of lava erupted. So this is showing that the cumulative volume of Mount Rainier in cubic kilometers. So see, we really added a lot of lava to the cone at that time. And then we went through a period where we didn't have as many eruptions, not so much lava erupted. And then again, 300 to 200 roughly, bam, look at that, just lots of lava erupted. And then now between, 180 million, or excuse me, 180,000 to the present, we have just pretty low eruptive rate. So when the volcano does erupt, there's not a lot of lava coming out. So important, you're going to see this again too, but for here, I'll just point out that these eruptions, the lava doesn't go everywhere equally. It's not equally distributed around the cone, but probably because of the topography, the lava would flow one direction one time and another direction another. And of course, we don't know what's underneath the younger layers. So, okay, so here we go. You can see this dark purple happened, greater than 500,000 years ago. It's over by Panhandle Gap and a little bit up here by Carbon Glacier. And then after that, we had a lot of lava flowing to the north. And after that, lava flowing mostly to the south, although a little bit to the north. And then to, maybe more broadly between 180 and 280,000 years ago. More recently, to the south and to the north. And we've actually had some lava flowing within the last until about 1,000 years ago, like just right at the summit with really, really small lava flows. Okay, so here's a big picture geological event. So it's just everything I just told you is just summarized here. We won't go over it all at the moment. You can go back and look at it yourself. But I do want to point out that, a million years ago, I mean, what are we talking about in terms of human time? That's roughly, when when the human species, people we would call, human, were on the planet. 500,000 years ago, it's roughly when Neanderthals were, um, and almost, when we're separating themselves as a different race from the Homo sapiens, other Homo sapiens. So, um, and then it goes from there. But you're going to be looking at another table later on that shows more recent stuff that we can really relate to more. So we'll just let it go with that and let you look at that later if you want. Okay, Module 3. There are stories within these rocks, and rocks, we see them everywhere. At Mount Rainier, you look in the riverbed and you see rocks, brown, gray, black, speckled, non-speckled, and you think, oh my gosh, there's such a variety. But and they're just plain old rocks. But actually, they tell a lot of stories, and you can tell a lot of stories to the visitors by knowing a little bit more about what we're learning within these rocks. Okay, and everybody gets a rock kit when they're a kid, right? Or at least in 8th, 9th grade science, everybody gets a rock collection that you're supposed to look at. And I always think, oh, that's a little bit of a waste, because people are just asked to identify rocks. They're not asked to understand the meaning of how they were formed. But it's like to me, those rock collection boxes are like a Whitman box of chocolates. You open them up and there's a story inside each of those chocolates. There's raspberry in one, raspberries that grew in a field, and there's cream from a cow in another, and coffee from a coffee bean in another one. So, there's a big story. So I urge you to take a look at the rocks around Mount Rainier and figure out what you can about them and talk to visitors. So, couple of activities. Magma Mash is one. Rock Stars. We'll take a look at a couple slides here. Those are in the Mount Rainier Educator Guide. So 2 big kinds of rock you're going to be seeing. Andesite, granodiorite. Almost exact same chemistry, but very different appearance. The granodiorite is the rock that never made it to the surface. It stalled down below the surface. The magma took a long time to cool, and therefore the crystals got big, and they're visible, and you can see them. And you can see, lots of feldspars with this white, but you also see these, these little black, there's pyroxenes and amphiboles. You don't have to remember all these, but just know that, it's each of the crystals had, probably hundreds of thousands of years to cool, or maybe longer, and so they got really big. But the same rock, when it's erupted out of the volcano, does not have those crystals in appearance showing. This particular rock in the picture here has some red on it, and I'll explain that later. Okay, so really important for you to know, because when you go out there in the stream bed looking at the rocks, like you see here, some I found in the Nisqually River, rocks of the same composition, the same chemical composition, can have very different appearances. It really depends on what's happened in the cooling process, and and that depends upon where it is in the lava flow. So you can actually tell which rocks were formed at the surface of the lava flow, which rocks came from the center of the lava flow, which ones came from the sides, which ones were subject to steam. For example, okay, so inside you get this lava that is flowing, and it keeps on flowing even when the outer part of the lava flow has cooled and hardened. It keeps flowing on the inside, and you get lots of fractures forming as it cools. And so you tend to get these very platy looking appearances of rocks. And you can see this really well over by Rick Sucker Point. You can see it up on the loop trail up above Paradise. You see the rocks with this really platy cleavage. All right, and then on the sides, you get the rocks cooling relatively quickly, and as they do, they form these no, it's not always octagonal or hexagonal. These columnar joints, and this is where we have the lava coming in contact pretty quickly with cool temperatures, either ice right next to it from glaciers or the cool air. So this is over by on the road to sunrise. Okay, some places the lava cools so quickly that it just flashes into a glass, and you can see it doesn't allow much light to escape, like in this piece of almost obsidian-like rock. And there are rocks over by sunrise that they have the same general appearance as obsidian. It's not obsidian, but the point is that it cooled really quickly, so it's probably on the outer surface. Sometimes we have rocks that uh, form on the surface uh, in the presence of steam, and so they oxidize, and we get the reddish color. All right, here's a gray color, normal. And other times we have rocks that are subjected long-term to heat and volcanic gases, sulfur dioxide, for example, rising through the groundwater, the chemical recombination making a weakly acidic solution of sulfuric acid and taking what had been a solid rock like the gray one here and turning it into this orange crumbly rock. You'll find a lot of this on the west side of Mount Rainier. Right, so some interpretive messages about volcanism that, again, volcanoes have erupted here for a long time. Some magma cooled underground, such as the granodiorite of the Tatoosh Range. And the rocks of the Tatoosh, the granodiorite, are easy to spot because of the large crystal size. Um, you might, I guess they could be the Dalmatian of the Dalmatian rocks of Park with all the spots. Okay, and then rocks of similar chemistry can have very different appearances, as we just noted. All right, let's see the previous page. All right, now we're going to look at volcanic processes. And understanding these processes is going to help you explain to people how the mountain was built and what the hazards might be for the future as well. And one of the things that we recognize in creating this diagram, we put this together, a dozen plus years ago, is that yes, we have our lava flows, we have these avalanches of hot rock and gas pyroclastic flows, and an eruptive column of ash, and tephra, volcanic ash fall, and all that. But it's important to understand that these don't happen independently. They don't happen in an isolated way. But they're causative. So one happens, it changes the situation, and then other events happen because of it. For example, the eruption columns and lava flows, like especially steep-sided lava flows on steep-sided volcanoes, they fall down. And when they do, they become an avalanche of hot rock and gas that we know as a pyroclastic flow. And the pyroclastic flow rips up a lot of the snow and ice, making a lahar, a volcanic mud flow. And when that happens, it flows a long distance from the volcano. So that's going to be a really important interaction and sequence of events that we'll be talking about later on. Okay, so I'm going to talk about these processes really quickly. It's just easiest to talk about what it is, the impacts, and guidance. You can go back and look at this further if you wish. So I realize that Mount Rainier is built from the incremental accumulation of lava flows and fragmental rock debris. So you get these layers, literally hundreds of lava flows with rock rubble layers in between. And so they're generally partially cemented together by lava. Okay, so but the volcanic ash it's just bits of shattered rock. It falls at normal air temperature distance from the volcano. Often it occurs at the beginning of an eruption. So it irritates the eyes, because it's very abrasive. It's not poisonous to touch now after an eruption or even during an eruption. When it gets to a thickness of about 3 inches, which is an extraordinary amount, that's when we start getting roof collapses and such, but that's actually pretty rare. Okay, ash reduces visibility, as you can see in the picture of Yakima on May 18th, 1980, after ash fell in downtown Yakima, the lights came on automatically. So guidance is to reduce your driving and stay indoors. And for people, especially with respiratory difficulties, you want to make sure that you have extra medications and oxygen if necessary. And there you see some pictures of it. You can see how jagged the surface of an ash particle is. All right, so let's see. I think this is going to run. So this is here we have, uh, kind of weird thing there. Oh, sorry about that. Oh, I goofed. Yeah. I just turned that one off, but I don't know if I'm going to be able to recover from that. But what we're seeing is volcanic ash coming out of the
You hit
vent at,
the undo button. Yeah, hit that one.
yeah, there it is. I couldn't
There we
find
go.
it there. All right, yeah. So it's this one I want to remove. Yeah. Okay, let's try that one again. So here you can see at the very beginning of the Mount St. Helens eruption of October 2004, that eruption lasted until 2008, but you can see it through the thermal camera and visual that there is black rock accompanied by lots of light steam here. And here it is, moments later, you can see it comes out of a vent. We had watched the glacier, Greater Glacier on Mount St. Helens. We saw that there was an unusual crevasse fracture pattern forming, and then it turned into a hole with water in it, and we all called it the hot tub. We thought we were all going to go to the hot tub at some point. It never happened, and the eruption happened through that point instead. So obviously hot rock is just below the surface. And so this might be how an eruption at Mount Rainier begins. It's not actually fresh magma coming out, but it is just loose surface rock that is being, blasted out of the volcano. Okay, we call it a phreatic eruption, by the way. All right, so at Mount Rainier, there is this really complex record of pumice, like all this pumice is the tephra that is or volcanic ash, whatever's tossed from the volcano actually have different sizes, but the pumice is the stuff that has bubbles in it. So there's this complex record. There are like, 40, 50, 60 layers of pumice in the park. It actually looks a lot like beach sand. And you think, well, gosh, was there a beach here at one time? And the answer of no, it's not. It's just this all this fragmental material that is out of the volcano. And you can see it all here, but not all of it is from Mount Rainier. Some of it has come from other Cascade volcanoes as well, such as this layer from uh, Mount St. Helens and others from another one from Crater Lake 7,700 years ago. All right, lava flows. Everybody knows about lava, right? And it's so important at Mount Rainier. Here is a Villarrica volcano in eruption in the early 1990s, and then the lower picture shows Mount Rainier. You can see that each of these is a lava flow. Wow. And Tom Sisson, who has done USGS scientist who's done a lot of um, climbing up and down these slopes, looking at the geology, mapping the layers, says that each one is roughly 100 feet thick. So there are hundreds of flows and each roughly 100 feet thick. That gives you some idea of scale. Right, so of course it's the partially molten or molten rock that flows or tumbles down the side of the volcano. The lava will just destroy everything in its path, and it melts some snow and ice. Sometimes it just melts itself into a deep trench, and as we'll see later, sometimes on these steep slopes it collapses as a pyroclastic flow. So you just need to keep people away. And when we have some chance of eruptive activity, a reawakening at Mount Rainier, we'll just have to make sure that people stay out. Remember these gleaming white magnets. I think such a great description. Really attract people. You wouldn't think people would be attracted to an erupting volcano and want to be close, but they do. All right, the other interesting thing at this picture of Villarrica, as I mentioned, sometimes it becomes entrenched. This is a glaciated volcano in middle latitudes of Chile. But the lava flowed down the side and entrenched itself and then just kind of stopped. And going there a few years later, I asked our guide to see these most recent lava flows, at which time they said, well, the glaciers just, after the lava flow cooled, the glaciers just rolled right over the top of them. And that actually probably happened with eruptions at Mount Rainier as well. Okay, so after we have the lava flows breaking apart they form these avalanches of hot rock and gas on the steep slopes, as this one at Montserrat. It's actually a lava dome there, but it's falling apart, making this avalanche really hot. Um, it has a cloud section and a lower basal section, and so it sweeps along the ground, will incinerate anything that's in its path. Yeah, people, houses, whatever. I doubt that this landscape is in existence now after many years of eruptions at Montserrat. So this can happen anytime during an eruption. When it can happen from lava flows falling apart or from eruptive columns falling apart, and you just cannot survive that. So again, the deal is to keep people away, and who knows, you as interpretive staff, you as rangers, safety personnel at the park, you may very easily have to switch hats, take off your Smokey Bear hat and put on your safety hat, and keep people distant from the volcano during eruption. Okay, so here is one example of a pyroclastic flow. Right, and it looks like it doesn't want to do this one. So yeah, so I'm going to make sure that you have each of these videos in case some of the clips don't work, and you can look at them on your own. Some of you may have seen them already, but basically this is showing a pyroclastic flow that sweeps over the landscape, Mount Unzen in 1991. Okay, now we're going to move on to another surface feature that's very important at Mount Rainier. Lahars and small seasonal debris flows. They're really somewhat one and the same. They're volcanic mud flows. They, when during eruption, they are going to be cool. Although there are reports from Mount St. Helens that in 1980 we did have some very warm debris flows and fish jumping out of the water and such. But what are they? Okay, debris flow, it's a mud flow, but it has so much debris in it. We tend to call them, as scientists, we call them debris flows. Lahar is a general name for that's used around the world for these features, these debris flows that happen on volcanoes. Here in the Pacific Northwest, we have worked with news media and other officials and decided that to keep the situation and keep our communication straight, we're going to talk about lahars as being the really big guys that move, for example, out of the park boundary and across areas where people are living now. So they're just these big slurries of mud, boulders, debris, houses, bridges, whatever gets in the way. They move frequently at 40 miles per hour down valley. And then where their valleys widen, the lahars are less constrained and they move out across the landscape. So they will destroy everything in their path by burial. And they fill in river channels. And this is very important because in doing so, they displace the water in rivers. And so the rivers flood out over the surface, causing flooding. And the sediment is carried downstream for years, decades, centuries after volcanic eruption. And will keep that flooding happening for a long, long time. There are places around Mount Hood, for example, that are still recovering from the 1780s, 1790s lahar activity there, where where a fresh channel still has not been incised to a depth that can hold that sandy river. Now, the one in the picture here is at Nevada del Ruiz volcano in Colombia, and this was a particularly tragic circumstance whereby an eruption happened, a small eruption happened at Nevada del Ruiz volcano, central Colombia. The people had been informed of it earlier on that this volcano was erupting, but they didn't have a full understanding of the circumstances. People said later that they did not know that um, that the volcano might even affect them if it went into eruption. And so when a small amount of volcanic ash melted snow and ice and made meltwater, it moved downstream and mixed with loose rock and made this big lahar. 40 miles downstream, it flooded the city of Armero, and 25,000 people lost their lives. It was a very sad circumstance, but it was also very telling. It has informed people around the world. Some of us have gone to Colombia to see this. Scott Beeson and I have been there. Scott's been there a couple times. So if you want to find out more about Nevada del Ruiz and the destruction of the city of Armero, talk to Scott more about it. Okay, let's see if this is going to run. All right, here is a Lahar volcano. Take a look. Mm. Okay, so that gives you some idea of the appearance of a lahar. Now, something I mentioned in the previous slide is that we do have small debris flows happening during summers at Mount Rainier, and they've happened quite a bit in the last the last 30 years or so. I think Scott Beeson is going to talk with you more about that. I worked on a major project there for better part of a decade on Tahoma Creek and Couts Creek, and Scott is doing great stuff now looking at debris flows and what causes them. So I'm sure he'll tell you more about that. All right, so what do those deposits look like? Well, if you're a fisher person and you go to any of the streams around Mount Rainier, you are going to see lahar deposits. Well, except if you go to the carbon. If you go to the carbon, you're probably not going to see them. But sometimes there's just a lot of loose, unconsolidated rock, and sometimes it looks like a rock wall that was built with cement between the boulders there. So, okay. It's a really common scenario during eruptions. Important for you to remember, just to review here, is that lava flows on steep slopes break apart, transform into avalanches of hot rock and gas called pyroclastic flows, which melt snow and ice and make a lot of loose meltwater, which picks up rock debris, makes lahars, which fill in channels and makes flooding for decades to centuries afterwards. Okay, some interpretive messages from this section is that the volcanic processes are really varied. There's a lot that can happen at a volcano. Some of these are ground processes, and others are airborne ash, such as volcanic ash hazards. They don't happen randomly, but in somewhat of a specific order because they're causative. Lahars are one of the dominant landscape changers at Mount Rainier and in the lowlands to come, as we will see later on. And lahars can affect valleys for centuries. All right, and then there are a few activities that I suggested there in the educator guide. You can go to them yourself. Okay, now let's look at some of the volcanic processes that have formed an impressive mountain, and they've also helped to create a habitable lowland in the vicinity of Mount Rainier. That is down valley of Mount Rainier. So recognize that this table shows a time from roughly 10,000 years ago to present, the last century. At the bottom, we have the end of the big ice ages. So, a lot of detail happened during the ice ages, during those eruptions, the same kind of stuff that you see listed here, but we will never know about it because the ice wiped everything out and wiped away the record, wiped the slate clean. And so, but we do know a lot more about what's happened recently. And so this is something for you to look at more on your own, but you can see that there have been eruptions, basically, maybe 4 different eruptive times, and then some reports of big steam blasts and such that happened. We don't know how believable some of these reports are, but you can see that there's been a lot of rockfall. There's a lot of mass wasting that's involved in these. Let you look at that on your own. But let's look at some of the really climactic chapters in Mount Rainier's story. All right, so we mentioned that the mountain has been accumulating a lot of lava rock, and it gets bigger and bigger, but doesn't stay that way forever. We're finding now that these very large volcanoes tend to fall apart through time, and we've seen it in Mount St. Helens, we've seen it at Mount Shasta, and perhaps 200 other volcanoes around the world. So that's happened at Mount Rainier as well. So one of the really big things that happened was 5,600 years ago when we had magma rising inside Mount Rainier. It destabilized the slopes and caused it to fail, and then the big lahar resulted from that, which went all the way down to the Puget Sound lowlands. Sometime between 500 and 2,300 years ago, we had a lot of snow, an eruption that caused a lot of snow and ice melt on the south side of Mount Rainier, which caused a lahar to travel all the way to the area of Puyallup and Sumner. On the White River, even 1,000 years ago, we had lahars flow down. The sands from those have been found in the port of Seattle, not the lahar itself, but sands that were carried downstream. And then about AD 1500, we had a major event uh, on the Puyallup River. So so that was known as the electron mud flow because named after the little town of Electron right here at the mountain front. Nobody knows about anymore, but it was a big power plant that was built back in the early 1900s. And this one was unusual because it did not seem to have happened. We can't find any evidence anyway that it happened during an eruption, and therefore we recognize that there is a particular trigger for this. What was that trigger? That's the question. We know that there was a lot of what we call hydrothermally altered rock. I mentioned that earlier with the rock stars reference, that the rock has been subjected long-term to uh, uh, acidic groundwater, and so it's become very friable, very unstable, and therefore can fall apart very easily. So the question is, what triggered this big electron mud flow of 1500? It was likely possible, that maybe there was some activity at the volcano, but no eruption happened, and that destabilized it. Or maybe there was an earthquake. We don't really know. Or maybe it was just long-term exposure to gravity that made that flank of the volcano fail. But at any rate, we do have, uh, we know that it traveled all that distance. Right, next one. Go back to the Osceola in this slide, look at it in detail. From 5,600 years ago, here you see the mountain higher than it is today, maybe 15, 16,000 feet. It's really not known. And here we have the bulge form that has fallen apart, and then we have a huge horseshoe-shaped crater remaining after the lahar descended. And then after that time, we have had regrowth of the volcano to its present height, not as high as it had been. And here's the culprit, that hydrothermally altered rock. Okay. Right, then let's go back to the electron mud flow, and you should note that the people living here at the time actually saw some of these events, and they put those events into their oral traditions, and we don't know for sure if it's the electron that they're talking about here, or maybe it was a different lahar, but we do know that they have in their record that Tacoba, the native name, one of the native names for Mount Rainier, Tacoba's head broke open and the lake on top spilled out and the water rushed down, and it filled the place where Ording is now. It filled the prairie and covered the prairie with bubble-filled stones, maybe like pumice or scoria. Here's the scar left behind, not just by the electron, but also by other earlier lahars as well. And I think it's important to recognize that a lot of people look at Mount Rainier, they see its glaciers, and they think, wow, those glaciers are very efficient carvers of the mountain. But actually, this is a scar from a landslide and not just by sculpting by glaciation. We talked about how we get all this sediment being carried downstream for decades and centuries afterwards. And that's visible here at Mount Pinatubo, which erupted in 1991. Very important to the Puget Sound lowland. I mentioned that actually lahars have made the landscape habitable in the lowlands, and that's because a part of the lowlands, the lowest areas of Puget Sound, were actually part of the sound underwater until after the Osceola mud flow. And after that time, and it took probably many centuries and perhaps millennia for it to happen, but material was carried downstream and filled it in. They filled in parts of Puget Sound. You know, the people living here at the time tell traditions of of hunting whales around where Sumner is now, where the whales would come down to this area. But that's obviously no longer possible, and this has been a major wetland now being filled in the last 50 years or so. We've, those of us spending time in the area, have watched this area being built up for industrial purposes. But all this is new land since the Osceola mud flow. All right, now you've seen this diagram before, but I added something to this version. At the bottom here, it says, you know, this whole time when Mount Rainier has been growing, we've had an ice age, and I meant to cut it off right here at about 15,000 years ago or so. I realized I didn't do that here. Okay, so Mount Rainier and the landscape was pretty much enveloped by ice for pretty much all of the mountain building era for Mount Rainier. Not to say that the era is over, but it's a fact that the area was covered by ice, as you see here inside this aqua blue circle. And so everywhere we stand, you know, during different glaciations, all of the park was covered or part of the rock was covered. And we can talk later in other presentations more about the details of those glacial features that you can actually still see. And understand, while Mount Rainier was under construction, there was the big ice age Puget Lobe coming south, and here it's in this area right here. So alpine ice met Puget Sound ice right along the foothills here. Okay. Right now, there have been some interesting interactions that have happened between the ice age glaciers, and the lava flows. So we call the ice age glaciers the architects of Mount Rainier. Today, smaller glaciers are more sculptors of it rather than architects. And let's look at the reason why. We've had many far traveled lava flows. You know, we had some pre-existing landscape, obviously. Maybe the landscape was non-glaciated during some parts of the larger Pleistocene, you know, ice ages. Maybe not. Maybe it was subglacial valleys that were formed. But anyway, some of the ice was very thick, and to the side of it, we had areas not so thick or even exposed ridges. When there were eruptions, the ice tended to flow down and remain, the lava flowed down and remained in the areas where the ice wasn't so thick or where it was non-existent. Right? Now here it is right here, sorry. Here to here. Okay, there it is. And then after the ice thinned, those lava flows remain high on the ridges. And that's happened not just once, but probably many times. And so you get somewhat of a pancake stack, a linear pancake stack of lava flows, one upon the other. One place where you can see that very well is not far from where many of you are at Longmire, where you can look at the Emerald Ridge lava flow. Let's see, that would not be, no, that's not the Emerald Ridge, that's a Rampart Ridge. It's a Rampart Ridge, X that, Rampart Ridge lava flow. And where you stand on the meadow floor, it's perhaps 800 to 1,000 feet. Would have been that far under ice at some point. Okay, so there's a lot of complexity here, but overall, lava filled in the regions between the thickest glacier ice. The result is these ridges like spokes on a bicycle wheel. Okay, so let's go through here quickly and look at some of these lava flows, just pointing out. You can look at them later. Here they are listed: Rampart and Emerald, you know, Mowich Lake, Spray Park, Graham Park, Burroughs Mountain, where Sunrise exists, Callis Park, Paradise Ridge. All those are lava flows. So when visitors come to the park and ask you where the lava is, where the lava flows are, and you're at Paradise or you're at Sunrise, you can say you are standing on a stack of lava flows. Okay, let's get to know module number 6. Let's get to know some of these geologic features at Mount Rainier. Again, that should be Rampart Ridge lava flow from Longmire Meadow. The Osceola mud flow, a big event. You can actually see from sunrise. You can see the area that fell between, and it was between Little Tahoma and Russell Cliffs over here. This whole area is where the Osceola mud flow emerged, and now this area has been rebuilt. Okay. Little Tahoma Peak is, side remnant, as just mentioned, and you can go, if you're climbing, you can see some of the pyroclastic flow deposits there, and you can see some dikes, these vertical, somewhat vertical, tabular um, areas where rock, where magma rose and then cooled in place inside the volcano. You can see the summit craters, and the most recent evidence of eruptions was, roughly 1,000 years ago, 1,100 years ago. You can see the summit craters. We do not know when the relative ages of each of these. They might have happened just days apart. They might have happened years or centuries apart. But here on the Emmons Glacier, we have a beautiful little lava flow underneath the ice, which raised the ice level. You can see there it is. And that's the youngest. This is the youngest lava flow on Mount Rainier. The old climbing route on Gibraltar is an erosional remnant, of that, of the Paradise Lahar. Paradise Lahar was it was kind of the south moving part of the Osceola mud flow. Anyway, it was left behind, and even just last night I was reading early accounts of climbing Mount Rainier, and this was their climbing route. And they talk about there being an overhang and the rock being very loose and rock just falling all over the place. So here, this is the old climbing route. So they eventually abandoned that in the early 20th century, and then the new route was formed over, or was decided upon, went into use over on Disappointment Cleaver. Willis Wall and Liberty Wall. So these are these like 3,000 foot high head walls. The Carving Glacier is on top, and it's down below. There's lots of avalanching up here, but look at these lava flows. Each of these benches being one. There's hundreds of them. Okay, Emerald Ridge. We're really on Emerald Ridge now, right along the Wonderland Trail near Tahoma Creek. And here over at Burroughs Mountain Lava Flow over by Sunrise, you can see the columnar jointing here, mentioned earlier. At the Emmons Glacier, there's a terrific amount of geologic treasures that you can point out here. You can note the Little Tahoma Peak being the southernmost sidewall left behind after the Osceola mudflow patch. You can see rock debris from the December 1963 rock, which insulated the glacier. You can see little ice age moraines. I mentioned big ice ages, but there were many small cooling periods and very minor ice ages that happened as well, even after the big one was over. On the west side, you can look at the Sunset Amphitheater and see the scar of the electron and other lahars, and they have exposed a kind of a museum piece of layers left behind by previous eruptions. The Tatoosh Range, remember that this is consists of rock, which mostly consists of rock that was cooled below the surface. The rock above it has been eroded, and therefore there's that granodiorite is at the surface now. The Nisqually Trail from the Moraine Trail, Nisqually Glacier from the Moraine Trail. Just a beautiful place to go, and where you can see the layers of lavas. You can see the carving by glaciers, and of course observe a glacier on its own. So there's so many interpretive messages we could say here, but some of the highlights is that much of the mountain building at Mount Rainier happened during the ice ages. Glaciers are architects and the sculptors of Mount Rainier. The big glaciers were architects, the small ones, maybe the sculptors. Volcanic processes transformed the Puget Sound lowlands into a landscape we know today, and evidence of Mount Rainier events are visible all around the park. So go to the Egg Guide for that. Let's see more about it. Okay. All right, so this is the last one, and this is a fairly lengthy presentation, but just overall, try to cut to the chase on this, but if we were all meeting together, we would be going outside and looking at rocks and looking at maps and such in the intervening time, but you're getting it all at once. So here goes. So we work with the premise that when people become knowledgeable about the natural processes, they can prepare and they can live with greater safety, and comfort. So we want to talk to people about volcano hazards, and people are going to come to Mount Rainier and they're going to ask about it. They're going to say they heard about it, they saw it in National Geographic or whatever, and with your uniform, you're going to be expected to have some answers. So dive into a little bit, and let's take a look at the eruptions and the Cascades overall as a starter. So here is the Cascade Range. Um, just a section shown from the Canadian border, not those above, down to the southern extent in Lassen Peak in California. And here's a timeline 4,000 years ago to the present. Good for you to be aware that this is not when the range began to form. We just made it 4,000 years because it makes a nice time frame on a poster, right? Each of these little volcanoes indicates that not just a single eruption, but probably a whole series of eruptions. And this is roughly a time 200 years ago. You can see that we've had 7 different volcanoes erupting just since a little before when our country was founded. This is an active volcanic range. We can expect that we will see more eruptions in the future with it. There's so much going on. And we call Mount Rainier an active volcano. You're going to hear that repeatedly. We call it active not because it's erupting. It's not. The most recent activity, 1,100 years ago or so, 1,000 years ago, reports of maybe steam eruptions, steamy explosions or something in 1894, 95. We don't put a lot of credence in those reports, frankly. But recent activity, being seismically active with earthquakes and hydrothermal activity, hot springs and steam, location on a subduction zone, the magma still forming. For all these reasons, we call it active. And we think that it could reawaken at any time. We don't have any evidence saying that it will be soon or whether it will be in a distant time, but we know it will erupt. With virtual certainty, what will happen when it does erupt? Well, Mount Rainier has a wide range of possibilities. It could be just minor eruptions of steam and ash right up at the summit here, get everybody all frightened, basically, and then nothing happens. Or it could be a large eruption that sends hot rocks down the slopes and forms lahars that come down to the lowlands, and that's kind of the worst case scenario. At present, very important to say, there's no signs of any volcanic unrest. When there is some unrest detected, the scientists will increase their monitoring efforts. We are in constant conversation with the park staff, with park management, and we will you all be notified very quickly. The public officials will let the public know as well. Right, so these are the areas where we think the lahars can happen in the future. The area, first, let's mention that the area that's shown in green here, a little red over top in some places, that's the area where we can expect lava flows and pyroclastic flows. We're not going to expect them distant, not like hardly even out of the park boundary. So it's really the lahars and more than 100,000 people who live on the previous lahar deposits that are at risk today. Now, the mountain doesn't make it easy for us. When a volcano reawakens, so many different things can happen. And of course, people need to make decisions. Public officials, people living in harm's way need to make decisions. But it could go into an eruption right away. It could go back to sleep without having an eruption and make us all look like we were crying wolf. It could go for a long period of time, for months or even years, or maybe even longer before it goes into eruption. Or it could just have a raised level of activity and go back to sleep with never an eruption happening. So somewhat like with humans, all the vital signs are present that these are active volcanoes. Just like with humans, sometimes it sleeps and tosses and turns, it erupts, other times it sleeps, lots of sleep, right? But when there is some sign of reawakening, that's when we really need to move into full gear, and in terms of getting people out of the way, increasing our monitoring and our communication. It might unfold. How might an eruption of Mount Rainier unfold? It could be, extreme steaming and earthquake activity and potentially some deformation of the slopes. It could be like at the summit of Veniaminoff volcano. You can see here in the photo. It could be like what we see also at Veni, where we have lava streaming down the side. You can see red hot lava flowing with volcanic ash and some cooling lava flows and a lot of melting of glacier ice. We can expect that there'll be lahars, as we see here in the picture of Mount St. Helens in 1980. This isn't the lahar itself, but this is perhaps a day or so later after lahar was draining its water. There it is flooding over the valley floor. We can expect volcanic ash from the summit being blown by the winds. It's going to reduce visibility. It's going to be gritty and conductive. It's going to be resuspended for months after the eruption because of human activity and winds. And but only if it's to extreme depth is it going to threaten buildings, and that could be the case within Mount Rainier National Park. When we compare Mount St. Helens with Mount Rainier, we can say that Mount St. Helens is much more of an ash producer. Mount Rainier is more of a lava flow maker. And so we don't expect a Mount St. Helens sized ashfall event from Mount Rainier, although it could happen, but it's unlikely. All right, we can expect lahars coming down the valleys. And as you see on the right from New Zealand, on the left from Mount St. Helens, um, change is expectable here at the park, and even in non-eruptive times. And that's a point that you need to keep in mind. Volcanic eruptions are survivable when precautions are taken. Preparedness is a collective process. We all need to do things that take actions to prepare. Volcanoes give us warning signs, but we need to have the monitoring equipment there. If we don't have the monitoring gear on the mountain and nearby the mountain, we're not going to be able to give good, efficient warnings. So we are looking for emissions of gases, additional earthquake activity, and swelling of the volcano. What should you be telling the public? Well, we suggest that you tell them to learn, inquire, plan, and prepare. Learn whether your community is in a volcano hazard zone and understand how your community might be affected. Inquire of the community officials, see what plans they're making. Prepare today. That means being ready to leave your home if told to do so, or to stay in your home for an extended period of time, like we all are in the pandemic right now. So it could be any of those. Depends on where you are. What messages should you convey prior to an eruption, volcanic crisis? If there is a lahar, you need to get off the valley floor. You need to move to high ground. You saw the map with the yellow zones where lahars could travel, and you need to get up off the ground, off maybe 50 to 100 feet off the valley floor, preferably walking. And I just took this picture in traffic going up towards Edgewood, Bonnie Lake one time. You can see, that everyone's going to want to go up, evacuate the valley floor by car. It's not going to be possible. So a lot is going on. We have volcano hazard work groups that were developed after we saw what happened at Mount St. Helens in 1980. And we have evacuation plans in some areas. We have long-term community outreach in progress. We have the educational resources referred to. The evacuations of school districts has actually been going really well in the area that we feel is most likely to have to suffer from unheralded lahars, those that happen even without an eruption, like in the Puyallup Valley, where there's a massive amount of hydrothermally altered rock that yet can fail. The Ording School District evacuates 3,000 students and teachers once or twice a year. Last year, we did a major evacuation with the Puyallup School District. They were the ones in charge, of course. We aided it, and they did very well. There were, I think, 8,000 people evacuated at that time. So at this website, you can find the evacuation routes, and I urge you to take a look at that. The public often wants to know how they'll be notified. And, again, scientists, the public officials, and the park management work together. We try very earnestly to get information out to the media. They are very happy to talk about volcanoes. There's NOAA weather radios, a siren system in the Puyallup and Carbon River valleys. So nothing going on right now. But I think it would be good for you to take a look at these alert level systems, understand what the different alert levels are. You can do that on your own. Visit our website, go to USGS Volcanoes on Facebook, and you can also sign up to have updates, weekly updates sent to you, or emergency updates sent to you as well, if necessary. Lots of information is on the website. There's a volcanic ash webpage. Go there and learn more about the effects of volcanic ash and how to clean up after them, and live comfortably even with volcanic ash around. So this is not the end. We know more eruptions will happen, and we just need to be ready. So, and you're playing a very important role in working with visitors, so many of them from areas that could be affected. Okay, thanks a lot. Again, my name is Carolyn Driedger. You can reach me at driedger@usgs.gov if you want. And I think there might be a Q&A session next week, and we'll hope to see you there. Thanks. Bye.
Awesome. Thank you so much, Carolyn. Let
You're
me
welcome.